careful. If you're doing an experiment, don't say you're happy with the amount of statistics when you have big peaks out here. Look there. In fact, one of the most, I guess, important experiments I ever did was, and I actually didn't do it, Peter Brentano and a student in Cologne did it, was to measure one of these beta decay spectrum for 3 or 4 weeks. Now, I think they left a source in front of the detector and went on vacation, but he claims they did it intentionally. Anyway, the point of it was they got infinitely good statistics and found the non-existence of a gamma ray there, because the statistics were so good, and that was really key to a model. Okay, so always look down here at the low energy transitions, which are the hardest to see, and pay attention to those. Okay, so now today, click the add title. Okay, so far we've dealt with cases of a few nucleons in a single J orbit. We talked about residual interactions affecting the energies of those levels. What happens when we start filling proton and neutron shells with more and more particles? Okay, so first let's talk about configurations. So if we have a set of nucleons, protons or neutrons that can fill certain orbits, the question we immediately have is... Oh, sorry. Thank you.
Oh. Sorry.
Did anyone see that number?
97.
No, don't. Okay, configurations. So let's say we have a set of nucleons that can occupy certain orbits. Once you have more than one nucleon, you have to ask what angular momentum they can couple to. We talked about that already yesterday with the M scheme in a simple case. And you know for that if I have 2 particles in H9 halves, they can couple to 0, 2, 4, 6, or 8, right? You could all do the M scheme and tell me that. Okay. Notice that there's only one configuration of each J value. Okay? There's only one 0 plus state, only one 2, only one 4, and so on. So what are the effects of the residual interactions? They can shift the energies, we saw that yesterday, but they can't mix any wave functions because you can only mix states of the same angular momentum. And so there's no mixing that occurs here. Let's take another example. 2 neutrons that we allow to occupy either, I'm sorry, I edited this part later and forgot to change that. I'll do that before we put it up. H9 halves or D5 halves. Okay, this should be D5 halves. Okay, so for positive parity, we can have 2 configurations. We can have H9 halves squared, in which case we get J equals 0, 2, 4, 6, 8. Or we get a D5 halves squared where we get 0, 2, 4. Okie dokie? All right. So now, you'll notice there are 2 ways of making a 0 plus state, 2 ways of making a 2 plus state, 2 ways of making a 4 plus state, and 1 each for 6 and 8. So if we have a residual interaction, it can mix the configurations of the 0, 2, and 4. So that's a non-diagonal effect of residual interactions in addition to any energy shifts. Okay? And so that becomes important once you allow particles to occupy multiple orbits. Okay, now I want to go through an exercise. And I want to ask you a question. Down here, when the slides raced through, there was a number in a box. Did any of you see that number? Are you being honest?
The screen was blank when it was flying.
Okay, good. Okay, so as you increase the number of valence nucleons, the number of ways of making a given state grows very rapidly. And I want to go through a couple of cases. So let's consider 2 particles in a D5 halves orbit. How many ways can you make a 2 plus state? Don't be influenced by the answer. There's one way, right? They can couple to 0, 2, or 4. What about if you have 4 particles that can occupy a D5 halves or G7 halves state? Now, I didn't do this very carefully. I don't know the exact number, but I wrote down 7 ways you could do it. There might be more. You could have 2 particles in D5 halves coupling to angular momentum 2, and the other in G7 halves, coupling angular momentum 0. Can you all see this, by the way, back in the back? Okay. You could have two particles in D5 halves coupled to angular momentum 0, two particles in G7 halves coupling to angular momentum 2. You could have two particles in D5 halves coupling to angular momentum 4, and two particles in G7 halves coupling to angular momentum 2, and then couple the 4 and the 2 to 2, going like this. You could have two particles in D5 halves coupled to 2, two particles in G7 halves coupled to 4, couple that to 2, and so on and so forth. Okay? And I wrote down 7 ways. I don't know if they. Okay? So here we have 4 particles in 2 orbits. We can make at least 7 configurations. So if you have a residual interaction, these 7 configurations will mix to a greater or lesser extent depending on the interaction. The wave functions will begin to develop some kind of correlations in collectivity. These 7 configurations will not all be at the same energy. It will take a different amount of energy to put 2 particles in D5 halves as it would in G7 halves, or to have 2 particles in D5 halves and 2 particles in G7 halves. So these initial levels will not be degenerate. And some of them will mix and some won't mix depending on the residual interaction, excuse me. So this is a little like that second Mathematica matrix, or the Mathematica matrix you had to do. They're not degenerate levels, they're not all equal interactions, but you will still begin to develop this correlated collective state where one state tends to come down low, and other states do something else. Okay. Now, here's a question. Suppose, this is a very famous example. I didn't do it. 154 samarium. It has 62 protons and 92 neutrons. The nearest closed shells are 50 and 82, so it has 12 valence protons and 10 valence neutrons. The valence protons will allow to fill this 50 to 82 shell. The valence neutrons, the 82 to 126. And the question is, how many 2+ states can we make subject to the Pauli principle? And I want you to guess. So if you know the answer, a few of you know the answer. Mallory, you probably know the answer, right? We must have discussed this. I know Riley knows the answer. So you're not allowed to say it. And anybody, you may know the answer. So, Okay, so if you know the answer, don't say it. But I'd like you to make an estimate of what you think the answer is.
My first
be careful what you say. What do you...
The first time you asked this, I made totally wrong estimate.
Okay, good. I hope all of you are as wrong as he is. Okay, so somebody say something. How many 2+ states? I'm going to point to somebody in a minute. So somebody say something.
10 to the power 4.
10 to the power 4. 10,000?
I don't know.
Okay, good answer. Some other answer?
10 to the power 4.
What did you guess?
Right.
Or you were just commenting on his?
Yeah, 1 10 up to 10. I don't know.
Sorry? 10?
Yeah.
Okay. Another answer? Come on. You can't be... Just give an answer. Yes?
0.
0. Okay.
That's always a good. It's always 0, 1, or
It's fine, arbitrary units.
The answer is 1 in arbitrary units, yes. In units in which H bar and C and everything else is 1, it's 1. Okay, some more answers.
Way bigger than 10 to the 4.
Sorry?
Way more than 10 to the 4.
Way more than 10 to the 4.
Yeah.
Oh.
Okay, this side of the room is getting very aggressive. So what do you think over here? The worst you can be is wrong.
Yeah. It's really big.
Lots of things, hundreds.
Hundreds. Hundreds?
Yeah.
Okay. Somewhere in the back. Oh, over here in the back.
Count, just say 10 to the something power, and then someone will be right. I mean, just start from 2,
I like
1,
4.
Sorry?
4.
He's calculating.
10 to 12. 10 to 10. Really big number.
10 to the 10.
10 to 12, yeah.
10 to 12.
Yeah. So many.
So my 10 to
So we have numbers ranging from 0 to 10 to the 12. Okay. Should we just take the average? Okay, come on, one or two more answers. Something over here.
Go make an educated guess.
10 to the 6th.
10 to, who said that? 10 to the 6th, okay. And one from over in this region. You can't be more wrong than some of the answers already. You.
10,000.
What?
10,000.
10,000. He said that already, so you agree with him.
So there's
All right.
two data points there.
Now, I was worried that I would accidentally click this, so I put in a buffer. All right, here's the answer. 3 times 10 to the 14th. Okay?
If we combine the 10 over there and my 4, then it's perfect.
Yeah, if you take the product.
Yeah.
Okay. So, that's a lot. Okay, so for an exercise, I'm going to ask you to diagonalize a 3 times 10 to the 14th. Okay, the point is, we can't deal with this, at least not yet. Actually, show model diagonalization or diagonalization routines using some special techniques can now get up to what, 10 to the 11th, I guess?
10 billion.
That's 10 to the 10th, but I think
Yes, it's fine.
they can get even a little higher, maybe only in Spain. But in any case, let's imagine you could diagonalize this. And let's say I asked you to, so you did that, and I asked you to look at the wave function components and tell me the structure. Well, first of all, if I asked you to print out the wave function, there'd be no trees left in France. Okay, if I asked you to look at it, you'd be looking at 10 to the 14th components. It would be very hard to see anything simple. I'm not saying that's not a good thing to do. I'm just saying it's not a way to give you an intuitive feel for what's going on. So you need to do something else. And what we're going to talk about today are what some of these other things are.
Sir, how do you get this number?
I didn't. I found it out from Igal Talmi, who did it using group theory. And Pete could probably
Yes,
explain.
I will give tomorrow an estimate. It's not exactly this. To get exactly the 2 pluses, that is difficult. But to have the number in the M scheme, that's not so hard. So I will give the formula.
The real number, by the way, is 2.89 and then some other digits. It's known exactly. But so I got it just because someone told me. Okay, so how can we calculate this? Well, there are lots of microscopic techniques, shell model, ab initio calculations, Monte Carlo methods, all sorts of things that are making amazing progress in recent years. It's really been a tremendous success, and I just picked up one that I happen to have. These are some calculations using a potential developed at Argonne. And this is really an amazing amount of progress. However, you notice it only goes up to carbon 12. And so, for the foreseeable future, it's limited to pretty light nuclei. Okay, if you want to go and study zirconium or cadmium or uranium or whatever, you have to do something else, at least for the moment. And so that's where collective models come in. And they bypass this idea of all the nucleonic interactions. This is the macroscopic approach I talked about in my very first slide. They look at the many-body system as a whole with a shape, a structure, quantum number, symmetry, selection rules, and so on. And that's what we're going to discuss the rest of today. Okay. When there are multiple states with the same J, we know that they can mix with each other due to residual interactions. We don't know a priori what the individual unperturbed energies are. We don't know what the mixing matrix elements are. But from basic quantum mechanics, we know the general effect. Namely, that it'll tend to produce a low-line collective state, or more than one, with wave functions that are coherent. And the larger the number of states that can mix, the larger n is, okay, the more this collectivity will grow. Now, if you go back to that 3 times 10 to the 14th number, and if you imagine that all those 10 to the 14th states are degenerate, if you imagine the residual interaction mixes all of them equally, okay, You remember the calculation we did very early yesterday with the BE2? And we said the BE2 from the 2 plus to the 0 plus came out as n times any one of those. That would give us a BE2 3 times 10 to the 14th times what any one of the individual transitions would be. Experimentally, those numbers are about 200. Okay, so 210 to the 14th are quite different. And so a simple picture like this really can't, it's really a toy model. But it does contain the essence of the physics, which is what I hoped you would see with that little mathematical diagonalization yesterday. So this is an extreme picture, but the general characteristics persist. One state comes down in energy, it tends to be collective, it has enhanced transition rates. And so here I have a cartoon of how structure varies from magic to magic. You start off with this kind of 2 valence nucleon system where you have a high 2 plus and other close line levels. R42 is less than 2. You add some valence nucleons, you go through a vibrational regime where R42 is on the order of 2. You get to mid-shell and you get rotational spectra. And these arrows are the BE2s, and the thickness is proportional to the value. And so the thickness grows. And then once you pass mid-shell, you always count these valence nucleons to the nearest closed shell, whether it's above or below. So you kind of reverse the picture. It doesn't reverse absolutely symmetrically in real nuclei, but this gives you the idea of how it goes. And this is observed experimentally. Okay, so 2 plus energy comes down, R4-2 ratio goes up, the BE2 values increase. Very characteristic of shell evolution everywhere. Okay, so now how can we understand this? There are 2 basic approaches. One is geometrical models, which introduce a potential that depends on the shape of the nucleus. This is a different potential than the one we talked about yesterday for individual nucleons. That was a potential that depended on the radius of the particle from the center. This is going to be a potential that depends on the shape of the nucleus. And algebraic models, which invoke symmetries in the nucleus and use group theory and so on. I will discuss these today in, is Jan talking in the second week or third?
Second week.
So in the second week and then again in the third, will there be anything on algebraic models this week?
Yes, I will give on Thursday.
For fermions or?
In general.
In general, okay. So you will hear a lot about algebraic models in these 3 weeks, including from me in the third week again, with some practical calculations. But today I want to focus on geometric models. Okay, and there are 2. Each one has little brothers and sisters that are related to it, offshoots and so on. But the basic types are these 2. So we'll start with a vibrator. And I showed this slide yesterday. If you have a spherical nucleus which is not absolutely rigid, but has some softness to it so it can oscillate back and forth, you can get a quadrupole excitation with 2 units of angular momentum. And having an integer spin, it's a phonon. It satisfies both Fermi statistics. And we'll see what that means in a minute. And, whoops, maybe we'll see it sooner than I thought. I thought there was something else coming. Anyway, it will come. You can have more than one of these phonons, and as you saw yesterday, or at least as we said, you can make a 4 plus state, okay? But if you take 2 phonons with angular momentum 2, you might be able to make other angular momenta. Imagine you take a 2 plus angular momentum phonon like this and another one like this, you could make a 0. Maybe you could make other things. So the first thing we have to do is find out if you have more than one phonon, what angular momenta you can make. And we use the M scheme. But now we're using the M scheme for bosons, not for fermions. So the Pauli principle enters in a very different way. So let's go through this. This is for 2 bosons, 2 phonons, each with angular momentum 2. And so we again make this little table. Let's say that the first one can occupy magnetic substate 2. Okay? The second one can also occupy magnetic substate 2. They're bosons, not fermions. That gives you a total magnetic quantum number of 4. You can also have 2 and 1, which gives you 3, 2 and 0, which gives you 2, 2 and minus 1 gives you 1, 2 and minus 2 gives you 0. Then you have to drop this, you can go to 1. 1 and 1 gives 2. 1 and 2 you can't do because you've got it there already. 1 and 0, 1 and minus 1. 0 and 0, and symmetric for the negative values, which I just don't bother to write. Okay? And now you look at this, and, well, you tell me, what can you say about the angular momentum states you can make? If you know the answer, I mean, I want you to get it from the table, not from knowing the answer. Yes?
4, 2, and 0.
How did you do that so quickly?
I looked at the table and I saw 4, 2, 1, 0, and 1, 0.
Okay, so
you have the highest.
all right, so you looked at the whole table. I want to just go a little step by step. You see the maximum magnetic substate is 4. So there has to be a spin 4 state. That spin 4 state has to have magnetic quantum numbers 3 and so on. There's no other 3. So you can't have another spin 3. So the next highest is 2. And as you said, you get 4, 2, and 0. Okay? So those are the 3 states you can make. It's an interesting thing. Remember we did like h9 halves squared with fermions, or let's say d5 halves squared with fermions. What would you get? 0, 2, 4. Same thing. Funny, huh? Okay. Anyway, so you can make 3 states. And we'll see what happens if you have 3 phonons in a minute. And this afternoon, you'll find out what happens if you have 4 phonons. Okay, so that means we can make 3 states, a 0, a 2, a 4, at twice the energy, because you need 2 of these phonons, as the 1 phonon state. So this is the kind of spectrum you would expect. Okay. I want to introduce creation and destruction operators. Do you all know about these? Is there anybody who has not encountered these? Okay, so I'll go very quickly through this then. So, what are these funny things called creation and destruction operators? Basically, they're ignorance operators. When you don't know the structure of a state, you can still learn a lot of things about it by using these operators as creating and destroying the state as a whole without knowing the detailed microscopic nature of it. Okay, with the dagger, it's a creation operator. Without the dagger, it's a destruction operator. I'm going to drop these subscripts because we're only talking about quadruple ones. The basic rules are the following. I think, Pete, will you derive these?
There will be an exercise.
Okay, so there'll be an exercise. So you guys will derive them. Okay, so a destruction operator acting on a state with n sub b phonons of type B gives you a state with 1 fewer phonon, because it destroys 1, and some number, square root of n. Creation operator acting on that same state gives you a state with 1 more phonon and another square root. Okay? Okay. An interesting quantity is this product operator, B dagger B. And let's look at what that does. So let's operate on a state with NB phonons with B dagger B. So just keep the B dagger over there and do B. So B acting on this will give you this formula, n sub B, n minus 1. Okay? This is just a number, so we can pull it out. And then B dagger operating on NB minus 1 will give you NB back, and it'll give you this square root. I'm just using this formula, but starting with NB minus 1. Okay, the square root of NB minus 1 plus 1 is square root of NB. So this gives you square root of NB times square root of NB times the wave function NB, which gives you NB times what you started with.
So you just did my exercise.
Forget you saw this. I thought you were going to have to derive these results.
Also, yes.
Okay, well, all right, so, I'm sorry. Okay, so it counts the number of phonons. I'm sorry. I showed you my slides before this. You obviously didn't look at them. Okay, so we can derive some interesting things from this. Let's look at this little scheme where we have 1 phonon, 2 phonons, 0, 2, 0, 2, 4. Okay, suppose I have a destruction operator acting between states with Ni initial and Ni final. If you go through this exercise, which is trivial now for you, you get the square root of Ni times a delta function, which is only non-zero if NF final is Ni minus 1. Okay? So this kind of matrix element only changes the number of phonons by 1 and reduces them. Okay? The transition probability, so this would correspond to a transition from an Ni, a state with Ni phonons to one with NF phonons, and it will only happen if the number of phonons in the final state is 1 less than the number in the initial state. The transition probability, the BE2, will be proportional to the square of this matrix element. So the BE2 value is proportional to the number of phonons in the initial state. Okay, so now we can already make a prediction. If I define this BE2 value to be 1, then this will clearly be 2. Okay? If you want a physical reason why this works, here you have 2 phonons and you have 2 choices. You can choose to destroy either one. So you have twice the probability of doing it. Okay, so that's one prediction in this vibrator model, that these BE2 values should be twice these. You have the selection rule we've already talked about, that you can only change the number of phonons by 1. You have a branching ratio, which we've already discussed, namely this over this is 2. And you have the result that transitions from this 2-phonon state to the ground state, which change the number of phonons by 2, are forbidden. Okay, so some very simple predictions of this model. Okay, now, what happens if we have, I will show later, actually I'm going to add in a slide during the break, which I meant to add in showing you how this works in a real case a little better, which I meant to do this morning, but I forgot. What happens with 3 phonons? Okay. Anybody want to do the end scheme in their head? I mean, here are the final magnetic substates. So what spins do we have? If you know the answer, don't just say it. I mean, get it from the table. What's the highest spin you can make?
6.
Okay.
4.
What's the next highest?
4.
Next highest?
4.
Okay, you can make 6.
4. What's the next step?
4.
So 6 has to use up magnetic quantum numbers from 6 down to 0. So 6, 5, 4, 3, 2, and I've got to pick up a 1 and a 0 somewhere here.
64321.
Sorry?
64320.
How did you do that so quickly?
I just put it.
Okay, you didn't know the result.
No, sir.
Okay. Okay. So the answer is 6, 4, 3, 2, 0. 5 states, known as the 3-phonon quintuplet. Okay? So these are the 5 states you can make. Okay? Here is a level scheme for cadmium-110 experimentally. Okay? And remember, no nucleus is ever going to look exactly like these idealized models. Okay, but here's cadmium-110. You have a ground state, naturally. You have a 2+ state at about 600 kilovolts. You have a set of 4, 2, and 0 at an energy about, let's see, this is 658 kilovolts. That's 1547, so it's a little more than 2 to 1, about 2.2 or so to 1. A nearby 2+, 0+ is pushed up somehow, okay? And it's typical that the levels are not, these should be degenerate in the pure model. It's typical that they're not, but these are relatively close together. They're within 200-300 kilovolts, which is half of the phonon spacing. Okay? Then you have a set of states which look like a 3-phonon state. Just 1 second.
Okay. So
6, 4, 3, 2, 0. You have a set of phonons which are, a set of states which look like 4-phonon, 5-phonon, and so on. When this was first developed, it was considered shocking because, and I'm not going to go into this, but if you think about the microscopic, I talk about these as vibrations, but you also have to always think of what's going on at the nucleon level. And these vibrations correspond to exciting nucleons from one orbit to another. Now imagine that you're going to put a particle from a d5 orbit into an s1/2 orbit. Just imagine that that's a major part of one of these vibrations. Well, once I've done it twice, I've filled that s1/2 orbit. I can't do it a 3rd time. So people didn't expect these 3, 4, and 5 phonon states to exist. And then level schemes like this were found, and it was pretty shocking. And the BE2 values, and that's the slide I'm going to add in, the BE2 values are not terrible. They're not perfect at all. And there's still a lot of controversy about whether these are really good vibrational nuclei. There's at least one group that claims not, so that's truth in advertising. My own opinion is yes, but okay, there's disputes. But what you see are these beautiful multiplets that look like phonon states. Yes?
So I was just wondering, because this spectra is very, the level scheme is very equidistant, and when you analyze the data and look at the spectra, this spectra will have like a bunch of lines just bunch to each other.
Yeah.
Doesn't this make it a little bit hard to analyze?
So you're asking an experimental question, right, about the spectra. You're saying that this transition, this, and this, they'll all be roughly the same energy.
And
And
what
so
people do?
the peaks may overlap.
Yeah.
Yeah. If you use germanium detectors, which have, say, 2 kilovolts,
Yeah.
well, let's say 1/10 of a kilovolt precision and 2 or 3, let's say 3 kilovolts resolution,
Yeah.
generally speaking, you're okay. Okay. You can also use a technique.
No, okay, but people before that, like which year was this discovered? Because I think within the 50s and
15,
50s there was
15, 20 years ago, the 90s. No, these higher phonon states only in the 90s.
So because people didn't have good germaniums.
No, germanium detectors came in the late 60s.
Mhm.
In fact, the very first thing I ever did in physics was to build germanium detectors. Take a piece of germanium and make a detector out of it. I did that with a guy named Joe Allen. Has anybody ever heard of Joe Allen? No. Sick transit. Okay, he did a thesis at Yale on light nuclei, SD shell, silicon, sulfur, looking at deformation and so on. And then he left the field and became an astronaut. And he went around the Earth hundreds and hundreds of times. And on the second moon landing, he was the person in Houston who was the communicator. So many of us our age have actually heard his voice without probably knowing it. Okay, anyway, that's off the topic. Germanium detectors have been around for a long time. And you're pretty much okay. You can also use technique of coincidences. You can, I'll get a little technical here for you. You can gate on a transition like this, and then you won't see the 6 to 2, you won't, okay? So you can do gating, various gating techniques to simplify the spectrum. You can do multiple gates. So you can sort it out. And if you do the experiment at a place like the ELL in Grenoble, they have detectors that are called crystal spectrometers, which work by diffraction. And they can get these energies to an electron volt. Okay? Yes?
So it seems you can predict the even spacing, but is there any way to predict what this effective frequency of vibration is?
Oh, you mean the absolute scale?
Right, like being able to predict omega naught here.
Yeah, no, well, I don't mean no, of course not. I mean, there's a difference between a collective model and a microscopic model. A microscopic model meaning nucleons and their interactions. Collective models, almost invariably, you cannot predict the scale. Okay, you have to put that in. Okay, with microscopic models, the scale should come out. If you do, okay, I'll do techno talk for a second. If you do an RPA calculation, for example, you should be able to get the energy of the phonon state. Okay? Right, at some level of accuracy. And the better the theory, the better you can do it. So, also, you should be able to get these non-degeneracies. Okay? Other questions? All questions have been good so far because there's no such thing as a stupid question.
Well, I was wondering if there's maybe some nice intersection of light to medium nuclei where you can kind of hit them both from an ab initio and collective perspective and compare.
Okay, so I was about to nod yes. When you said ab initio, there you got a little bit of a problem. Let's talk about microscopic, which could be large basis shell model calculations, where you still take a core. Maybe you take a nickel 68 core or something like that. And yes, in that region, roughly mass 60 to 100, People are doing large basis shell model calculations nowadays and getting, I think, reasonable results. Would you agree?
Yes, but like this example would be very hard in the shell model, for instance.
Because of the orbits involved.
Yes.
Yeah, yeah.
So,
But like for example, in the zinc isotopes, that region, those are simpler. I think the answer is yes. You have a comment? Okay? Okay. So this is a real spectrum of a nucleus that seems to look quite a bit like a vibrator. And I will put in a table of the VE2s because I think it's worthwhile seeing them because it gives you another feeling for how good or bad these idealized models are. Okay. Now, gamma ray transitions. This is, I mean, seeing the energy levels is one thing, but you always want to look at transition rates. They're very sensitive. Remember, the selection rule is you can create or destroy a single phonon. And so these transitions are allowed, but that one is forbidden. And so one of the obvious things you would do is you'd look at the ratio of this gamma ray intensity to this, correct for the e to the fifth factor, and see what the ratio of the E2 values is. Okay, I want to... I want to make a comment about these three phonon states now. There's an interesting facet of these, which may not be obvious at first. Let's take a three phonon state of angular momentum 2. You can make it three different ways. You can couple two phonons to 0, and then use the third to make 2 plus angular momentum, like this. You can take two, well, I'll do this one. You can take two and couple them to 4, and then anti-align the third one to make angular momentum 2. Or you can couple two of them to 2, and then couple the third, make angular momentum 2. These are three independent ways of making a three phonon state. Now imagine a transition, an E2 transition from a three phonon state to a two phonon state. You can destroy the third phonon in any of these cases. And so speaking of lawnmowers, I knew I was going to be in Europe for 6 weeks, so I went to the barber and asked him to cut my hair short. My hair doesn't normally look like this. He went crazy. Okay. Anyway, so you can destroy any one of these phonons, which means this 2 plus state can decay to a 0 plus state by destroying this phonon. It can decay to a 2 plus state by destroying this, or to a 4 plus state by destroying this. Okay? And so we can end up with all of these. Somebody remind me to put an E there. Okay, and this is what you get. And I know you're going to do this, right, Pete? With your CFPs?
I will discuss it.
Okay. All right. So, remember, if this is 1 unit of transition strength, these transitions from the 2 phonon state are 2, the transitions from the 3 phonon state should be 3. And so here you see the 6 plus, which decays with 3 units of the E2 value to the 4 plus. The 2 plus can go to the 0, the 2, and the 4 with these relative BE2 values. Now, I'm not deriving these, I'm just telling you. If you add up these, you get 49 plus 20, they're all over 35. 49 plus 20 is 69, plus 36 is 105. 105 divided by 35 is also 3. So in this case, the sum of the 3 BE2 values gives you 3. These particular ratios can be derived with a technique called coefficients of fractional parentage, which Pete will talk about tomorrow. Okay. And so what you would look for in the experimental spectra are not only 3 transitions from this level to these 3, but with relative BE2 values taking on those numbers. Okay? Okay. Oh, I took out a slide. Okay. I wanted to show you another one. It doesn't matter. There are some other examples where... Let me comment on these selection rules.
One remark if you go back. These states are not independent, huh?
No, but there are 3... Okay. There are three independent ways of making it.
Of making the
Yeah.
same scale.
Yeah, yeah,
That
okay.
is-
All right, sorry, you're right. So I wanted to show a nucleus here, which I, for some reason, deleted the slide. It's cadmium 118, which shows these relative DE2 values and shows that the ratio of the forbidden ones to the allowed ones is on the order of 20. Oh, well, 1 over 20. So the forbidden ones are a few percent of the allowed ones, which means that at that's the level at which the model works. It's predicting that it predicts that the forbidden ones are 0, and in fact they're 3 to 10% of the allowed ones, and that's relatively good agreement. And that's, by the way, if you do any kind of analysis of a spectrum and compare with theory, when you talk about theoretical uncertainties, you have to fold that kind of idea. Okay, now I want to talk about deformed nuclei. So I'm making a big switch in topic here. What time is it, by the way? Oh, okay, we got plenty of time. Okay, so now I'm switching to deformed nuclei. So I've covered what I want to on spherical nuclei. Are there any questions on those? Is your hand up or you? No. Well, you were sort of like this. Any questions? Tends to ask. Okay. Is it clear so far? Did someone say no? Huh?
No, it's good.
No, it's clear.
No, it's
Okay.
It's okay.
It's okay. Am I going too fast?
Yeah.
Am I going too fast? Am I going too slow? Oh,
Why is it that in real life this phonon model is not perfect?
these models are so extremely simplified. For one thing, I actually gave you a reason already. If you think about making these phonons microscopically in terms of particles, okay? Let's take the simple model I talked about. Let's say you have particles, the ground state has the d5 halves orbit filled. And let's say there's an s1/2 orbit up here. And let's make a trivial example where making a phonon takes a particle from d5 halves to s1/2. That will have angular momentum 2. Good. Okay? And now let's say I make a 2-phonon model. That means I superpose 2 of these. So I take 2 particles out of d5 halves and put them into s1/2. Now let's say I make a 3-phonon model. I take 3 particles out of d5 halves and I put them into s1/2. I can't do it. s1/2 is filled. So the 3-phonon state has to have a modified wave function. Now that component of the phonon, d5 halves to s1/2, may only be 10% of the phonon. There will be other components. But that part will have to change. And so the structure of the phonon as you go up in the spectrum will be modified. Okay? The amazing thing is that it works at all. Okay?
So shouldn't the angular momentum of the phonon, which, you know, we're treating them like bosons, we're just going from 0 to 2 to 4, wouldn't it be determined by the single particle angular momentum that we're pushing the particle through?
I would say it the other way. If you want to have a quadrupole phonon spectrum, that limits which particle excitations you can have in it. They all have to have angular momentum 2.
Okay.
So you have to change the angular momentum by 2. You could go from s1/2 to d5 halves. You could also go g7 halves to g9 halves because they can couple to 2.
So depending on where you are, this conservation of angular momentum could really determine the energy jump of this single particle.
Sure, absolutely. Absolutely. So here's something to think about while I'm talking. Think about the collectivity of these states depends on the number of different ways you can make that angular momentum. Okay, and it's more collective, lower line, the more ways you can make it. Think about collectivity of octapole vibrations. Now don't get distracted while we're talking, but just put that in the back of your mind. Okay. Don't lose the rest of it. Okay. Okay, is that clear? I mean, I'm not discussing the microscopic structure of these phonons, but you have to always realize there is a microscopic structure. The microscopic model and these collective models are not incompatible. They're just different ways of looking at the same thing, and they have to be compatible in the end. Okay? To me, the amazing thing is they work at all. It's like the joke with the guy who went into the bar with a dog, and he said to the bartender that this dog is amazing, he can talk. And the bartender said, "Ah, come on." He asked the dog, "What's 2 plus 2?" And the dog says, 5. And the guy says, "The dog is stupid." So the owner says, "No, the amazing thing is he can talk at all." So the amazing thing is that these models work at all. They are so simple. Okay, and I'll make this point later when we talk about Oliger rules. Yes?
The angular momentum of a fauna is equal to 2. Is our definition, or is it derived from something?
No, we're trying to understand states which have these angular momentum 2 characters. Okay, you could also do it with angular momentum 3. You could have octupole phonons. Okay, now for reasons that, don't tell me. Winston? No. Did I get it?
No.
But I'm close.
Yeah.
It's 2 syllables. It's 2 syllables.
2 syllables. The last syllable's relatively correct.
So what was it?
Justin.
Justin, okay, Winston, Justin. In first order, that's the same.
Yeah.
Okay, so he's actually thinking about this while we talk. So you can have other kinds, you can have hexadecable with angular momentum 4. But there are reasons why these are not very common. And we'll talk about that later. Okay, that's a good question. Okay? All right, so, whoops. So now, deformed ellipsoidal nuclei. Okay, nuclei can have non-spherical shapes. And I'm not going to get very formal about this, but I just need to introduce these 2 variables. So here's an ellipsoidal nucleus. And this axis is longer than this. And that elongation, that deformation, is usually parameterized in terms of a quantity called beta. You'll often see beta, people will say the deformation is beta is 0 point whatever the value. Okay? There are, by the way, in the literature, other notations for this. There's epsilon, there's delta, there's even eta. You guys probably will never encounter eta, but in the past it was used. They're all, if you see an epsilon or a delta or a beta, they're all the same within about 5%. They're slightly different definitions. Most people use beta. And then there's another parameter, or not parameter, but variable, called gamma, which is the axial asymmetry. And what I try to illustrate here is, I colored this yellow because I'm looking end on now. And the nucleus, if this is the first one on the left, okay, if I squeeze it like this, then that's axially asymmetric. And that angular dependence in this way is specified by gamma. Okay, so, and you have a radius now, which is not just a single quantity as you would have for a sphere, but depends on beta and gamma. Okay? Now, obviously, you can make a model of nuclei like this in a geometrical sense by having a model which has a potential which is expressed in terms of beta and gamma. And we will look at that very briefly toward the end of the morning if I get to it. Okay? And it'll have some interesting aspects to the discussion. Okay, so I want to collect a bunch of things here. So first of all, if we have a deformed nucleus, and I look at the change in radius relative to the sphere of the same volume in the z direction, which is always the elongation direction, the y direction and the x direction, these are the formulas from the previous slide. Okay, and here I collect some numbers. So gamma equals 0, no, oh, by the way, there are different conventions for gamma. Gamma equals 0 is always an axially symmetric prolate American football type nucleus. The shapes for these other gammas, they're different conventions. Okay, I'm using a convention where 0 is prolate, 60 is oblate, and 30 is the most axially asymmetric. Okay, so for gamma equals 0, delta RZ is +1 in units of these square roots. And delta Rx and delta Ry are equal and half as much. So what that means is you take a sphere, you elongate it in this direction. To conserve volume, you squeeze it in this direction and squeeze it in this direction. Okay? If you go to 30 degrees, then all 3 directions are different. So that's axially asymmetric. Okay, that means that you have, well, I think it's clear. If you go to 60 degrees, whoops. If you go to 60 degrees, RZ and RX are equal and positive, and RY is the opposite sign. So an oblate nucleus, so this is a prolate, here's a better prolate nucleus. This is a prolate nucleus. An oblate nucleus is shaped like a disc, like a frisbee, okay? And if you think about getting from a sphere to a frisbee, you have to elongate it in two directions and squeeze it in one. For a prolate, you have to elongate it in one and squeeze it in two. So that's the difference between prolate and oblate. Namely, in a prolate nucleus, you elongate it in one direction, squeeze it in two. Oblate, you elongate it in two directions to make a disc, and you squeeze it in one. Okay, so that gives you some feeling for the shapes. Okay. Moment of inertia. We've already encountered the moment of inertia when we talked about rotational formulas. Remember the energies went as h bar squared over 2I times jj plus 1. So here's I. Now, you all know what the classic moment of inertia for an object is. It's mr squared, the sum over infinitesimal elements of mr squared, or for a rod it's mr squared. Mr squared. R squared is the distance squared. M is the mass. Okay? For a nucleus, the mass is the number of nucleons times the mass, and that it goes as the radius. So the moment of inertia goes as a to the 5/3. Okay? Here's 3/3, and r is a to the 1/3, so r squared is 2/3, so it goes as a to the 5/3. Okay? That means as the mass of the nucleus increases, the moment of inertia will increase. It depends on beta. Where's beta? 1 plus 0.31 beta. And this has an important implication for looking at data. We talked about R42, and this is one of the reasons why it's so useful. In R42 with less than 2, you immediately know something about the nucleus. An R42 value near 2, you know something about the nucleus. R4 value of 3.33, you know something about the nucleus. Measuring E2 plus doesn't tell you anything about the nucleus, because the energy formula is this. And you don't, unless you know what I is, E2 plus is not invariant over the nuclear chart. And that's why in the rare earth region, the best deformed nuclei have 2 plus energies around 80 kilovolts. In the actinides, they're around 45 kilovolts. But a nucleus with a similar shape in magnesium is 800 kilovolts. So some of you yesterday looked at magnesium-32 and saw that the 2 plus state was at 800 kilovolts. And you said, oh, that's high. It can't be deformed. Got to be careful. 2 plus energy, the absolute value of the 2 plus energy is not mass invariant. Okay, so, and that comes directly from this moment of inertia. Okay, quadrupole moments, they go as beta, and then a correction factor, which is usually pretty small. Typical values of beta are 0.3, as we'll see in a minute. And so 0.16 times 0.3 is 0.05, so that's pretty small. So quadrupole moments are proportional to the elongation. And BE2 values from the first 2 plus state to the ground state, I'm not deriving this, I'm just telling you, go as the quadrupole moment squared, which means they go as the deformation squared in first order. And that, these two facts here allow us to deduce something very nice. But first, first let me, I want to look at these BE2 values just experimentally for a moment. So you've seen this plot already. They're very, very small for magic nuclei. They're very big for collective deformed nuclei between magic numbers near mid-shell. From these values, using this equation and this equation, we can actually experimentally extract beta. And so...
one question.
Yeah.
For the quadrupole moment, is it correct that it's linear in deformation because we have beta times, and in the brackets there's again beta, so it should be squared?
Well, this is going to be beta.
Yeah.
And that's going to be beta times about 0.05. Beta is about 0.3.
Yeah.
So 0.3 times 0.16 is 0.05
Yeah.
compared to 1. So that's why I say in first order it's linear.
Okay.
There are corrections.
I didn't get the first orders.
Can I ask also something about the B2? Because
Yeah.
usually, somehow, I always think of quadruple moment as the diagonal matrix element. And so the quadruple moment of the ground state would be like the diagonal matrix element of the ground state. And it's kind of the B2. So going from the 2+ state to the ground state depends only on what is the quadruple moment of the ground state. It doesn't tell us anything about the 2+ state.
This formula assumes that the shape of the nucleus is not changing as you go from one state to another.
Yeah, because it's it's a rigid rotor. It's
Exactly.
rotating and
Okay? Okay, so what I want to do now is use this data here, this region, to actually extract values of beta. So I have this expression for the quadruple moment, I ignore that. The BE2 value is this formula which I gave you. The formula I showed you, it comes from this thing with a Klebsch-Gordon coefficient. And so from this and from this, I can get that the BE2 goes as beta squared, or beta goes as the square root of BE2. And so from the measured BE2 values, being careful about these constants, I can actually extract beta 2, or beta as I've called it. And you get, these are typical values that you get across the rare earth region. Okay? They're small at the edges, near the closed shell. They go up to typically a little more than 0.3 in mid-shell. Notice they don't go to 0 at the closed shells. If I put lead on here, lead is a doubly magic nucleus. It would not be 0. And that has to do with 0-point motion. We'll get to that later. Okay? Now, nuclei that are deformed, not only can they rotate, they can also vibrate. There's no reason why they can't vibrate. And so the levels of a deformed nucleus will consist of a ground state, vibrational states, and rotational sequences built on top of it. And we've seen that. You saw this already, but now I want to go, you saw a very simplified version of this, without this stuff, okay, and without some of the other stuff I'm going to put up here. Now I want to go into this in much more detail. So there's the ground state. Fortunately, nuclei have ground states. Here you have a set of rotational states. By now this should be very familiar to you. 0, 2, 4, 6, 8 that satisfy this formula, approximately. And what I've done here is I have fixed h bar squared over 2I to match the energy of this 2+ state. So remember somebody, Justin, was asking, can you predict h bar omega? So it's the same thing here. In a collective model, you can't predict what h bar squared over 2I is going to be. Okay? You have to feed the model some information. So here I feed it some information by normalizing this. And then I predict these states. Okay? And
How close do you get if you just use that real crude I is proportional to A to the 5/3?
On a relative scale, let's say the moment the rotational spacing's in mass 100 compared to mass 150 compared to mass 230, you do okay. I don't actually know what on an absolute, I haven't calculated that.
That sounds like a good exercise.
Could be. You can add that in. You can do that one. Okay. Let's look at these numbers, the comparisons. What do you see if you compare these two sets of numbers? Is the agreement good or bad? Is it perfect?
When you go higher in the excited state, then the experimental value is a little bit lower than the
Experimental values are always lower than the theoretical. So, first of all, when you see this, what you should say, or what I think you should say, is this is remarkable agreement. I mean, think what we've done. We've got a nucleus with 150, how many? 164 particles, and all we've done is say it rotates, and we get these states to within a couple of %. It's not too bad. Not too shabby. Does everybody know that expression in English? Not too shabby. It means good. Yeah? You ever good? Okay. Now, you see there's some differences, though. Okay, why?
I think if we stay in the same framework, so we can imagine, like, I think this model is sometimes called a liquid drop model. So when we rotate a faster liquid, this liquid gets maybe pushed a little bit outside. So the moment of inertia, so the mean square radius grows a little. So the moment of inertia also grows. So
But that
the
was,
spectra also gets a little bit closer. So the effective moment of inertia arises. So that's why our real data is a little bit lower than the
Okay, interesting answer. Yeah?
could we add in some vibrational effects?
What do you mean by vibrational effects?
Well, right now we're just rotating, but as you said, rotors can also vibrate.
Okay, good. Other answers?
You're assuming rigidity, but that's not fully the case.
Is that different than?
yeah.
I think somebody over here said something?
Again, the rigidity.
I'm sorry?
H2 over 2R.
Just say it again, I
Yeah,
didn't.
the
You're agreeing?
Yes.
Okay. Okay, actually, you're both right. The order of magnitude of the effects is a little bit different. Vasily, right?
Yeah.
Yeah. His explanation was pretty much, okay. There are some people who are going to tell me it has to do with structure and pairing, but I'm going to ignore that. What you said basically is a centrifugal force.
Yeah, I say, let's say in the same model.
Yeah.
We
As
assume
the
that it's a
nucleus,
liquid
as
drop.
the nucleus rotates, if I go like this, or if I go faster,
Yeah.
okay, I'm going to spread out.
Yeah.
And so the radius will increase, moment inertia will increase, and the energies will drop. Is that clear? Now, your comment about vibrations. So if you think about what that really means is, there are vibrational excitations. We're going to talk about them in a minute. And what your comment is equivalent to is saying that they can mix with the ground state, or with this ground state band, and that these states will have some admixture of these wave functions. They will be vibrating a little, right? And that's absolutely right. It turns out in practice that effect is typically less than a kilovolt. But the effect is definitely there. Okay, so the main reason is centrifugal stretching. Okay? All right. Now, here we have vibrational excitations, which I already introduced this name because I wanted you to do that exercise. Okay, this is called a gamma band, and it corresponds. Okay, stop him. This will be the last slide before the break. It corresponds to an oscillation like this. Okay? All right, and it has angular momentum 2. We'll talk in a minute about why it has angular momentum 2. And then it has a rotational band built on top of it, 3, 4, 5, 6, and so on. Here are the energies again, and I've normalized this spacing. And again, you see that these spacings are really quite well. There's something funny here, and I don't understand that. But typically they're lower, maybe I wrote that down wrong. They're lower than the predicted ones. And then you have another excitation here, which has 0 angular momentum. I haven't introduced the K quantum number, but don't worry about that. And again, it has a rotational band built on top of it. This is sometimes called a beta vibration. And the idea of beta and gamma vibrations were introduced, as far as I know, by Bohr and Modelson. Bohr and Modelson also proved that beta vibrations can't exist. And so I hesitate to call them beta vibrations. And if you want me to go into why they can't exist, we can. But in any case, almost all deformed nuclei have a low-lying state with angular momentum 0 and a rotational band built on top of it. And whether you call it a beta, I will tend to call it beta vibrations just because I grew up that way and I can't stop my mouth from saying it. But I'm not really implying a specific. A beta vibration would mean an elongation like this. Okay, but anyway, those are the states you get. And this gamma is squishing and beta is elongation. These are rotational, I already said that. These are rotational states built on that. And note that the wave functions of all these states have both intrinsic and rotational parts. Okay? In other words, the ground state has a certain structure. These states are simply rotational motion superimposed on the ground state. This has a certain intrinsic structure, and these states are rotation superimposed on that. And the same thing here. By the way, an odd mass nuclei is much more subtle. And I don't, well, maybe I'll get into it in the third week. Depends if I have time.
On top of that.
Okay? So they have an intrinsic part and a rotational part. That will be very, very important later on. It relates to the exercise you did on Erbium 168. Okay? I think, okay, I will tantalize you with this coming up, and let's stop here. Okay, let's have a coffee break. Other degrees of freedom. Okay? I mean, if you imagine you're back in 1951 and somebody showed this level scheme, nobody in the audience would raise their hand and say, huh? Why isn't that 333? Because you don't have the paradigm. Once you have the paradigm, then you can start looking at small differences like that and learn something. So these idealized models, even though they're not exactly followed by real nuclei, are still extremely valuable. Okay. What I want to do is now show you some data on, let me go back a little, some data on these vibrational modes to give you an idea of how they behave across the nuclear chart. Okay, I define the nuclear chart as the rare earth nuclei, so from mass 150 to 190, simply because there's more data there than anywhere else. This is the energy of the gamma band. Okay? And the main thing you see here is how smooth it is. Now I draw this line here because something else is actually happening over there. But here in this region, it behaves very smoothly. And that's the essence of a collective state. Remember, the collective state is the one that comes down as a mixture of many, many components in the wave function. And so if you change, if you have a collective state which has 100 components all in phase, and you add 2 nucleons, you're not going to change that a lot. Okay, the wave function is going to be pretty much the same. And so the behavior is very smooth and regular. Okay? For the k equals 0, here I call it beta, you have a couple of things. First of all, there's much more fluctuations, which tells you that thing is less collective. It's also higher in energy. It's averaged about, this is 1200 kilovolts, so say 1100 kilovolts, whereas this in the middle of the rare earth region is about 800. And remember, the more collective, the lower it goes. Think of the indegenerate levels mixing. The more levels you have, the more components in the lower state, the lower the energy. So you can see from that that this excitation is intrinsically more collective, okay, than this k equals 0. That should be reflected in the BE2 values, right? Remember we calculated very early yesterday, BE2, if you have n degenerate levels all mixing, one level comes down, and then we calculated the BE2 values, and we found they were proportional to n times the individual unperturbed ones. Okay? Right? Okay. So you would expect that this being more collective should have larger BE2 values to the ground state than this, than that, than this. Okay. This behavior here, we will understand in the third week after we study the Nielsen model. But the point I want to make now is it's very regular and smooth. And these, as I said, these excitations are about 1.5 times these in energy, and they fluctuate more, has lower collectivity. Okay. Here is a, yeah.
So what is that line?
This line?
How did you classify the data points?
Are you talking about this line?
No.
This?
Line connecting.
Oh, they're connecting isotopes of a given element.
Isotope.
Yeah. Okay.
Tutsographic.
I'm sorry?
How do you call Tutsographic? Just connecting the points with lines.
They're connecting isotopes of each element. So one of these will be erbium, another will be dysprosium. Is that what you're saying?
I mean, it's just looks a little bit strange, like you can extrapolate some stuff.
You're saying you can extrapolate these?
No, I say that
there is no extrapolation, you just connect
point.
Different isotopes.
This is data. This is all data.
Yeah, but it's not like really needed to connect them because it's like isolated point for this nuclei is this one. It's not in.
I don't have to connect them. I just did it so you could see the systematics. That not only is it smooth in general, but it's smooth for each Z.
It's not static.
All right, this is a very broad summary of all of these nuclei, just to give you a feeling for some of the values. BE2 values within this ground state band are typically 2 to 300 Weisskopf units. A Weisskopf unit is a certain measure of strength, which you can see defined in the textbooks. I wanted to put it here between the 2 to 0, but I couldn't squeeze this arrow in there, so I put it there. From the gamma band to the ground band, you typically have like 7 Weisskopf units, vary somewhat. From this k equals 0, 1, you have typically 1 to 2. These are experimental summaries of experimental results. This is just a leftover label from before I used those energies. But these are typical of most deformed nuclei. Okay, and so as we expected from the previous slide, these BE2 values are larger than these, they're more collective. And in fact, the gamma band behaves very regularly. Here's the actual data on those BE2 values. So here is the first 2 plus to 0 plus, that's the lowest transition in the nucleus. Very regular, typically about 200 Weisskopf units. Here's the gamma band 2 plus to the ground band, typically 5 or so, I think I said 7 before. And here is the k equals 0, 1. And first of all, you see it's much smaller on the order of unity, and also much bigger fluctuations. Okay? So this is a nice collective behavior, few Weisskopf units. This is much more chaotic and may or may not be really collective.
So I don't want to interfere lecture, but
no, you should.
Yeah, because I mean, we talk with him. We kind of get we know what's Weisskopf units, but do everyone knows what's Weisskopf units and what they show? Because I think you didn't define what.
No, I didn't. The Weisskopf unit is. It's defined.
I think it's good to define here.
It's defined in the literature. It's basically supposed to be a measure of what happens if a particle changes from one independent particle model orbit to another. So if you have more than one Weisskopf unit, it means a collective effect. Something is enhancing it. Now, in practice, in heavy nuclei, a single particle transition where a particle changes orbit would actually be a fraction of a Weisskopf unit. Okay, but you can think of it as a measure of collectivity. There's a definition, which if any of you have my book, you'll see in the preface or somewhere. Okay. When we talked about vibrational nuclei, we talked about multi-phonon vibrational states, 2 phonon, 3 phonon, even possibly 4 and 5 phonon. You can have that in deformed nuclei. So here's the ground band, ground state, gamma band, k equals 0. These are phonon excitations, just like in spherical nuclei. There's no reason you can't have 2 of them. So you could have 2, let's do this first. You could have 2 k equals 0 ones.
So, real quick, you defined k equals 0 as projection of angular momentum onto the
symmetry axis.
Symmetry axis, but what is the significance of k equals 2 and k equals 0? Like, what intuition should I be getting?
Okay, very good question. So, k equals 0 is easy for the beta vibration. It's an elongation like this. This is the symmetry axis. There's no angular momentum around that axis. Okay?
But for 0, you could also just be rotating perpendicular, right?
You mean this way? You can't rotate about a symmetry axis quantum-mechanically.
But if it's triaxial or something?
Oh, yeah, but we're not talking about those.
Okay.
We're talking about axially symmetric. So the beta vibration is an elongation like this. There's no angular momentum around this axis. Angular momentum around this axis would be a rotation like this. Now, the gamma band, that's a little trickier. And I need a nucleus. Good nucleons. Okay. So, this is what a gamma vibration looks like. Okay? Now, why is that 2 units of angular momentum around the symmetry axis? Because I can do that, I can also simulate by doing this. And so it's really a rotation around this axis. Okay? So now I can have multiphonon states. So I can have two k equals zeros that will also give k equals 0. And it would be called a 2 phonon k equals 0, or if I use this dangerous notation, it would be called a beta beta. It would be at twice the energy of the single one. Okay? I could have a gamma gamma. Now, these projection quantum numbers add algebraically. Angular momenta add vectorially. So if I have two phonons with k equals 2, the resultant will be either k equals 4 or k equals 0. So I can have two types of 2 phonon gamma vibrations at twice this energy. So k equals 0, k equals 4, gamma gamma. I could have a mixed beta gamma. Okay? The selection rules for the decay would be just like in the vibrator. These states, these 2 phonon states, can decay to the 1 phonon state, not to the ground state. So this state, this k equals 0 gamma gamma, can decay to the gamma. It can't decay to the beta, and it can decay to the ground. That's in the geometric model. Okay, the beta beta would go to the beta, not to the ground, not to the gamma. In the IBA, it's slightly different, but okay. All right, so what's the evidence for these? Well, pretty sparse. And there are a number of reasons for that. One is that these are, in vibrational nuclei, the phonon states, like in cadmium, are about 500 kilovolts. So a double phonon is about 1,000 or 1,100. Three phonons about 1,600, 1,700. The level density in even nuclei starts increasing very rapidly around 1,800 kilovolts. And experiments become more difficult. Isolating states becomes more difficult. Measuring lifetimes, BE2s, everything becomes more difficult. In deformed nuclei, I go back to here, these vibrational energies are 800, 900 kilovolts. These are 10, 11, 1,200 kilovolts. If I now multiply that by 2, I'm getting that the 2 phonon states are up at 1,800 kilovolts, 2,000 kilovolts. In this region where the level density of non-collective states is huge, and it becomes experimentally very parameter, which is x equals 2g omega over d. This is the interaction, and that's the spacing between the levels, and that is, I won't blow this up, I think you can see it. That is, remember we did 2-state mixing in the first day? That's essentially, that's 1 over my R parameter. My R parameter was the unperturbed spacing divided by the interaction. And so everything I did there, with these plots, you can translate directly to what he did. Okay? Secondly, he talked about B pair going as number of nucleons and the residual going as the number of nucleons squared. And if you remember, we talked about the P factor, which is number of valence protons, number of valence neutrons over the sum as a measure of the competition between pairing and proton-neutron interaction. It's exactly the same idea. This goes as n squared, this goes as n, and so that's exactly the same competition. So when I saw him write this, I immediately thought, okay, it's the same physics. And one other thing is, he talked about, and I want to make sure I get this right, Augusto, you talked about the Fermi surface as a function of nuclear number having a kind of staircase behavior in the absence of pairing, right? And then pairing smooths it out?
Correct.
Okay, and
that's one of the main features of the pairing is to smoother the.
And we talked about something very similar. Remember those two guys going off there? When we talked about 2 nucleon separation energies. And here you see throughout most of a shell these linear behaviors. You would think as you fill neutrons that you would fill neutrons at a certain separation energy And then when you start filling the next orbit, the separation energy would drop. The next orbit, it would drop more, and you'd have something that would go like this, like a staircase, but in fact, it's smoothed out by the interactions. Now, the fact that it's not smoothed out at closed shells shows you a point which Augusto made yesterday, that pairing doesn't totally dominate. It's really a competition, and when you have a big gap between single particle levels, you really see it. Okay, those are just a couple of comments.
Yeah, that in that plot, during the smooth part, x happens to be larger than 1, and near the closed shell, x becomes less than